welcome to the Data Science Interview Prep Podcast. In this series, we go through topics that are commonly discussed in data science interviews, and we give a high-level overview on those subjects. So in today's episode, we will be discussing the Naïve Bayes classifier, which is super important to understand in the field of data science. And whether you're preparing for a data science interview or you just want to refresh your understanding of Bayesian statistics and naive Bayes classifiers, this episode will hopefully be helpful and an eye-opener. All right, so with that being said, let's dive right into today's segment on the naive Bayes classifiers. So first things first, let's start off by discussing the overarching concept of something called Bayesian statistics. So now Bayesian statistics kind of serves as the foundation for understanding the naive Bayes classifier. And as you might have guessed from the name, Bayesian statistics is a branch of statistics that is based on the Bayes theorem. And what's special about Bayes' theorem is that it provides us a useful framework for updating our probabilities based on new data. And with Bayes' theorem, when we update our probabilities with new information, that's super helpful because it allows us to make more informed decisions in an uncertain situation. Essentially, the main idea behind Bayes' theorem is that we can update our beliefs based on new evidence. Now, we aren't going to deep dive too much into Bayes' theorem. Go ahead and let us know if you would prefer us to spend a dedicated segment on Bayes' theorem, but I do want to give you an idea of how the theorem is expressed. So basically, the theorem states that the probability of event A happening, given that event B has occurred, is equal to the probability of event B happening, given that event A has occurred, times the probability that event A occurs independently. We take all of that over the probability of event B occurring independently. Maybe if that expression didn't quite make sense to you, an example might help you wrap your head around things. So I want you to imagine that you're a detective trying to solve a murder mystery, and you have a bunch of suspects in mind, but you need to narrow them down. Well, you can narrow down your options by, let's say, gathering more evidence. Like maybe you can collect fingerprints, eyewitness accounts, anything to help you get a better picture of who the true culprit is. Now, with each new piece of evidence, you get more information about who the likely culprit is, right? In this case, you can use Bayes' theorem to help you update the likelihood of each suspect being the true culprit based on any of the new evidence that you keep on gathering. And in the end, after all of your hard work, the suspect with the highest probability of guilt, given all of the evidence you collected, is probably going to be your main culprit. So again, in essence, Bayes' theorem lets us update our probabilities based on new information. Alrighty then, so with this foundation in place, let's dive into understanding the naive Bayes classifier. So the naive Bayes classifier is a machine learning algorithm that is used in classification tasks. And maybe you already got that from the classifier being in the name. Now, you might be wondering why we call it a naive Bayes classifier. Well, the reason we call it naive is because it makes a pretty big assumption. So it assumes that the attributes of the data are conditionally independent given the class. And in simple terms, this essentially means that we assume the presence of one feature doesn't impact the presence of any other feature when considering the class, which is a naive assumption because this assumption is often not quite valid in real-world situations. But even though it makes this naive assumption, the naive Bayes classifier has still shown itself to be a surprisingly effective classification algorithm. Okay, do you remember at the beginning of this podcast where we talked a little bit about Bayes' theorem? Well, I told you that it would be helpful to understand the naive Bayes classifier. And the reason for that is because the naive Bayes classifier uses Bayes' theorem to update the probabilities of each class given the features of the input data. So to get the predicted output, we simply take the class with the highest probability. And to make sense of all this, let's try to visualize the model being used with an example. So let's say we're trying to classify emails as either spam or not spam. We have a bunch of emails with certain features. Those features might, for example, count the presence of specific words or typos and so forth. And now, if we have these features, how can we leverage this information to make a prediction about whether the email is spam or not spam? Well, using the naive Bayes classifier, we can calculate the probability of an email being spam or not spam given its features. Let's just walk through a high-level overview of the steps involved in that calculation. So in the first step, we're going to calculate the prior probabilities for each class. So that is, we're going to get the prior probability of spam and the prior probability of not spam. And for each of those features we discussed, for example, whether or not there's a specific word or typos, we can calculate the conditional probabilities given each class. So the probability of that word appearing in the email given that the email is spam, and the probability of that word appearing in the email given that the email is not spam. So for a new email, what are we going to do? We're going to calculate the probabilities for each class given the features of that email. So we'll check for the probability that the email is spam given the contents of that email, and also the probability that the email is not spam given the contents of that email. And finally, to get our output, we just compare the probabilities and predict the class with the highest class probability. So please do note that, of course, these steps are simplified to make it more easily digestible in a podcast format, but it still demonstrates the core concepts behind the naive Bayes classifier. And one thing to note is that in practice, the naive Bayes classifier can be applied to different types of data by choosing some appropriate probability distribution for the features you're working with. And for example, you can use the Gaussian naive Bayes classifier, which of course assumes that the features follow a normal distribution. And this type of model is typically used when we are working with, let's say, continuous data. We also have the multinomial naive Bayes, which is often used to assign text documents to some class. And of course, we have the Bernoulli naive Bayes, which is suitable for binary data where data can only take two values, like 0 or 1, for instance. Okay then, so before we wrap up, let's go over some practical tips that will help you with implementing your naive Bayes classifier effectively, and also review some of the previous podcast episodes that we touched upon. Okay, so first, some tips on data preprocessing. As you might know from our other episodes, techniques like normalization, standardization, and something we didn't speak about, but something can be very useful, binning, can all help to improve the performance of your classifier, depending, of course, on the distribution of the data and the classifier that you're implementing. We also had an episode on imbalanced data where we discussed techniques like oversampling, undersampling, and the use of synthetic data to help mitigate the effects of class imbalance. And finally, as with any machine learning model, it's really important to evaluate how your naive Bayes classifier performs on relevant metrics like accuracy, precision, recall, and F1 score for classification tasks. Okay, so with that being said, I think it's a good time to wrap up today's episode on naive Bayes classifiers and Bayesian statistics. Thanks for tuning in to today's episode of the Data Science Interview Prep Podcast. We hope you found this episode helpful and informative. Be sure to join us next week where we will discuss other interesting topics in the field of data science. Until then, happy modeling!